Plants are the foundation of most life on Earth. They harness the sun's energy to produce food, but plants don't exist in isolation. They depend on a complex and often overlooked resource soil. Soil chemistry, the study of the composition, structure, and properties of soil, holds the key to understanding plant growth and nutrition. Soil provides essential nutrients for plant growth. These nutrients are taken up by plant roots in specific forms and quantities. Soil chemistry dictates the availability of these nutrients, influencing everything from plant health to crop yield. Understanding soil chemistry allows us to manage this precious resource effectively. It enables us to optimize plant growth and ensure the sustainability of our food systems. Soil chemistry is a complex field. It involves interactions between the solid, liquid, and gaseous phases of soil. It also encompasses the biological components, including microorganisms and plant roots. By delving into the intricacies of soil chemistry, we can unlock the secrets to sustainable agriculture and environmental stewardship. Soil may appear as a simple, homogeneous mass. However, it is a complex system composed of diverse components. These components interact dynamically to create a fertile environment for plant life. The primary components of soil include mineral particles, organic matter, water, and air. Mineral particles form the skeletal structure of soil. They are derived from the weathering of rocks and minerals. These particles vary in size from large sand particles to tiny clay particles. The proportion of different-sized particles determines the soil texture. This texture influences drainage, aeration, and nutrient retention. Organic matter, derived from decomposed plant and animal residues, is another crucial component. It contributes to soil fertility by providing essential nutrients. It also improves soil structure, water-holding capacity, and microbial activity. Water is essential for plant growth and nutrient transport. Soil acts as a reservoir for water, holding it within its pores. The amount of water soil can hold depends on its texture and organic matter content. Air occupies the spaces between soil particles not filled with water. Adequate airspace is vital for root respiration and the survival of beneficial soil organisms. Beneath the surface, a hidden world thrives in the soil. This zone, known as the rhizosphere, is where plant roots interact with a complex web of soil organisms and nutrients. Understanding these interactions is crucial to comprehending plant nutrition. Plant roots release various substances into the rhizosphere. These substances, known as root exudates, include sugars, amino acids, and organic acids. These exudates attract and nourish a diverse community of microorganisms. These microbes, in turn, play crucial roles in nutrient cycling, disease suppression, and plant growth promotion. Nutrients in the soil exist in different forms. Some are readily available for plant uptake, while others are bound to soil particles or organic matter. The rhizosphere is a hotbed of nutrient transformations. Microorganisms decompose organic matter, releasing nutrients into the soil solution. The rhizosphere is also a site of competition. Plants compete with microbes for essential nutrients. This intricate interplay between plant roots, microbes, and nutrients highlights the dynamic nature of the rhizosphere. It emphasizes the importance of understanding these interactions for optimizing plant nutrition and soil health. Section 4. Nature's recyclers, organic matter and nutrient availability. Organic matter, the decomposed remnants of once living organisms, is the lifeblood of healthy soil, providing essential nutrients and improving soil structure. It plays a pivotal role in nutrient cycling, soil structure, and microbial activity, all of which are essential for plant growth and soil health. Understanding the types and functions of organic matter is crucial for sustainable soil management and long-term agricultural productivity. Organic matter exists in various stages of decomposition, each contributing differently to soil health. Fresh residues like fallen leaves and crop residues are gradually broken down by soil microbes, releasing nutrients back into the soil. As decomposition progresses, complex organic molecules are transformed into simpler compounds, which are more easily utilized by plants. These compounds include humus, a stable form of organic matter that contributes significantly to soil fertility and overall soil health. Humus acts like a sponge, holding water and nutrients, making them available to plants when they need them the most. It improves soil structure, creating aggregates that enhance drainage and aeration, which are vital for root development. Humus also provides a food source for beneficial soil microbes, fueling their activities and promoting a healthy soil ecosystem. The benefits of organic matter extend beyond nutrient availability, impacting overall soil health and plant vitality. It enhances soil's ability to buffer against pH changes, maintaining a stable environment for plant roots. It also improves the soil's capacity to retain and hold on to nutrients, preventing them from leaching out of the root zone and ensuring they are available for plant uptake. By promoting the accumulation of organic matter in soil, we foster a healthy and productive ecosystem for plant growth, ensuring sustainable agriculture for future generations. Section 5. The glue that binds. Soil colloids and cation exchange capacity. Soil colloids, tiny particles with immense influence, play a crucial role in nutrient retention and availability. These minuscule particles are the unsung heroes of soil fertility. These particles, composed of clay minerals and organic matter, possess a remarkable ability to hold and exchange cations, positively charged ions essential for plant growth. This interaction is vital for maintaining soil health. The surface of soil colloids carries a negative charge, which is a key characteristic. This negative charge attracts and absorbs cations like calcium, magnesium, potassium, and ammonium, ensuring these nutrients are available for plant uptake. This adsorption prevents these essential nutrients from leaching out of the soil profile, especially during heavy rainfall or irrigation. Cation exchange capacity, or CEC, is a measure of the soil's ability to hold and exchange cations. It is a critical indicator of soil fertility. It represents the total negative charge available on soil colloids, which determines how many cations the soil can retain. Soils with a high CEC can retain more nutrients, making them more fertile and productive for crop growth. The type of clay minerals and the amount of organic matter significantly influence a soil's CEC. Different soils have varying capacities. Clay minerals with a high surface area and charge, like montmorillonite, contribute to a higher CEC, enhancing soil fertility. Similarly, soils rich in organic matter exhibit a greater capacity to hold and exchange cations, further boosting their fertility. Understanding CEC is fundamental for managing soil fertility. It helps in making informed decisions. It guides fertilizer recommendations, liming practices, and overall soil health assessments, ensuring sustainable agricultural practices. Section 6. The pH puzzle. Unlocking nutrient availability. Soil pH, a measure of its acidity or alkalinity, is a master regulator of nutrient availability. Like a delicate puzzle, each nutrient has an optimal pH range for uptake. Understanding pH's influence is crucial for unlocking the full potential of soil fertility. A pH value below 7 indicates acidity, while a value above 7 indicates alkalinity. Most plants thrive in slightly acidic to neutral soils with a pH between 6 and 7. In this range, essential nutrients are generally more available. As pH deviates from this optimal range, nutrient availability can be affected. In acidic soils, the availability of phosphorus, calcium, and magnesium decreases. Conversely, in alkaline soils, iron, manganese, and zinc become less available. Soil pH also influences microbial activity. Many beneficial soil microbes prefer a near-neutral pH. Extreme pH values can hinder their growth and activity, impacting nutrient cycling and soil health. Maintaining an optimal pH through liming or acidifying amendments is essential for maximizing nutrient availability and supporting a thriving soil ecosystem. Section 7. The Rhizosphere, a microscopic metropolis of life. The rhizosphere, a microscopic metropolis teeming with life, is where the intricate interactions between plant roots, soil microbes, and nutrients culminate in a delicate balance. This zone, extending a few millimeters from the root surface, is a hotbed of activity, influencing plant nutrition, soil structure, and overall soil health. Plant roots release a cocktail of compounds into the rhizosphere, shaping the microbial community and nutrient dynamics in profound ways. These root exudates, rich in sugars, amino acids, and other organic molecules, attract and nourish a diverse array of bacteria and fungi, creating a bustling ecosystem. The rhizosphere microbiome plays a crucial role in nutrient cycling, breaking down organic matter. Microbes decompose organic matter, releasing essential nutrients into the soil solution, making them readily available to plants. Some microbes form symbiotic relationships with plants, enhancing nutrient acquisition and improving plant growth. Beneficial microbes in the rhizosphere also protect plants from pathogens, acting as a natural defense system. They compete for resources, produce antibiotics, and stimulate the plant's immune system, creating a protective barrier. This intricate web of interactions highlights the rhizosphere's importance in plant health, nutrient acquisition, and overall ecosystem stability. Understanding and managing the rhizosphere is crucial for sustainable agriculture and long-term soil fertility. By promoting a diverse and beneficial rhizosphere microbiome, we can enhance nutrient use efficiency, reduce reliance on synthetic inputs, and foster healthier, more resilient plants, ensuring a sustainable future for agriculture.